video number 3 on concave mirrors and the images that they form. Yesterday or previously in videos 1 and 2. Video 1, we went over some of the basic terminology, focal length, center of curvature, object distance, and so forth. In video number 2, we talked about what is true about the image when the object is way out over here, when DO is greater than the center of curvature. But also, I started asking you a question about what's happening as the object moves closer to the center of curvature. Okay, so today we're going to do that. We're going to move the object closer to the center of curvature until it is exactly at the center of curvature. One of the things you should have noticed, well, two of the things you should have noticed are, number one, the image gets larger as the object moves closer. You can see it reflected over in this box over here, HI. You can also see it literally by looking at the size of the image on the diagram here. So the image is going to get larger as the object moves closer, but also the image is going to move farther from the mirror. So as the object gets closer, the image gets farther. So we'll see that again as I continue to move this object closer to the mirror. As it gets closer, the image you can see moves farther away. Right now, the image distance is 7. All right. Now watch as I move the object closer. Now it's 7.2. The image height is 1.6. Again, negative because it's inverted. Watch as I move the object closer. The image height is 1.7. All right. And this continues to happen until the object is located precisely at the center of curvature. And you saw it kind of almost snap into place when that happened. And when the object distance is 8, which is where the center of curvature is, the image distance is also 8. In other words, when DO is 8, DI is 8 if the focal length is 4. So what I would like you to do right now is try that. Use your mirror equation, 1 over F equals 1 over DO plus 1 over DI, and plug in the right numbers. So when DO equals 8 and F equals 4, does DI also equal 8? In other words, solve for DI, knowing that the focal length is 4 and the object distance is 8. You should get 8. See if you do. See if you can get that math right. I'll give you a little time. You can pause, try it, and then come on back when you're ready. Go ahead. All right, now that you're back, let's try the magnification equation. When DO is 8 and DI is 8, if the height of the object is 2, which I tried to keep it pretty constant at 2 as I was moving it in, if the height of the object is 2, is the height of the image 2? Or should the equation tell us? Does the equation tell us that the height of the image is 2? Yes, 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 yes. I know, -2 because it's upside down. But really, the number is the key thing here because this tells us that the image and the object are the same size. One is flipped upside down for sure, but they're the same size. So again, I'm going to give you a minute. You can go ahead and pause it. I'm going to give you a minute to calculate using the magnification equation to verify this information over here. When DO is 8 and DI is 8 and the height of the object is 2, is the height of the image also 2? All right, take a moment and come on back when you're ready. All right, the last thing I'd like you to notice are the image characteristics over here. You'll see that the image is inverted when the object is located at 2 focal lengths. You can see that up here. The object distance is equal to 2 focal lengths, so the center of curvature. You get an inverted image. Of course, it's real, because if it's inverted, it's real. If it's real, it's inverted. Or in other words, reflected light rays actually intersect at that point. That's what real images do. And the height of the image equals the height of the object. Yes, I know it's negative because it's inverted. And the image distance is also equal to 2f, just like the object distance. The image distance and the object distance are the same. So those are characteristics that are true for this particular case when the object distance is equal to 2f. The next video I'll show, the next simulation I'll do, will show you what happens when we move the object in closer to the mirror than 2f, when the object is between the center of curvature and the focal length. But I think you can predict what is going to happen to the image when the object moves still closer to the mirror. You've seen what happens as the object moves closer to this point. Now, what's going to happen as it moves even closer? Before you view the next video, see if you can predict what's going to happen and then see if you're correct. All right. Thank you.